Welcome to density. We put some soda cans in a fish tank, and as you can see, some of them have sunk to the bottom and some are floating. But if you look real carefully, the ones which are floating are diet sodas. Now, why do you think that is? I'll let you figure that out for yourself, but I'll give you a couple of clues. First, read the label of ingredients on the can, and second, think density. Chemistry is the study of matter, and matter is defined as something which has mass and occupies space. The ratio of these two properties is called density, where density is equal to mass of a substance divided by its volume. Now, all matter has density associated with it. And furthermore, density is an intensive property. That is, it doesn't depend on the amount of material present, but only on the substance. Therefore, it can be helpful in identifying a substance. There are two general methods for determining density: flotation and determining individually the mass and the volume. Now, we'll be using today only using the mass and volume technique for determining density, but let's first look at some examples of the flotation method. The flotation method is used in such applications as measuring the charge in a car battery, and it's also used in winemaking to determine the amount of alcohol or sugar there is in the wine at any point. It uses this instrument called a hygrometer, which when put in a liquid will float in a vertical position, and the stem here is graduated in density units, so that the more dense the liquid, the higher this will float, and therefore the density will be read as being greater. In another example of the use of flotation to measure density, we have here some plastic which we have suspended in a solution of sodium sulfate and water, and then we have adjusted the density of that sodium sulfate solution until the unknown neither sinks nor floats on average. And then we have measured the density of the solution by pipetting out 10 milliliters and weighing it. The density of this solution is 1.138 grams per cc, which is also the density then of the plastic. Now, this is a very useful method where you have only a slight amount of solid. You can then suspend it, and instead of having to measure the trace amount of solid as far as weight or volume is concerned, you measure the large amount of solution in which it was suspended. Speaking of flotation, I have a couple of eggs here. One, as you can see, is uncooked, and I'm going to put it in the saline solution here. And the other is clearly hard-boiled. I'm also going to put it in here. And now, what is this telling you about the science of hard-boiling an egg? The difference between sink and float is very important commercially and not just in building boats. Mining companies use froth flotation to separate valuable components of ores. Cranberry growers take advantage of the berries' low density to harvest them. I'm sure you can think of other examples, but now let's switch to things more specific to what you'll be doing in this experiment. In today's experiment, you'll be measuring both the mass and the volume to determine density. Measure the mass of an object, you will be using a balance, and here we'll be using an electronic analytical balance. As you can see, it weighs to 4 decimal places in grams. That's an analytical balance. Now, to use a balance, make sure that it's closed, make sure that it's level, and above all, make sure that it reads 0 to start out with. Now, you will open the door and you will start weighing, and we'll be using paper clips in the demonstration here. And as you can see, the mass of paper clips is an extensive property. The more paper clips you put on, the more it weighs. Make sure before you make a weighing that you close the door. To measure volume, we'll use several techniques. If the solid is a regular object, you can measure its dimensions. We're using a ruler here in metric system, and from its dimensions and geometry you can determine its volume. On the other hand, if it isn't a regular object, or if you so wish, you can use a graduated cylinder. You put a certain amount of liquid, water for example, in the graduated cylinder, then put your solid in. If it doesn't dissolve and it sinks, then it will raise the level of the liquid, and the rise in the level of the liquid will tell you the volume of the solid. And also we'll be using something called a pycnometer. It has a stopper on top which has a hole in it. This is designed to contain an exact volume of liquid, and I'll show you how to use that later. And finally, if you have an unknown which is a liquid, you can use a pipette. Here we have a 10 milliliter pipette which measures out exactly 10 milliliters, and use that to determine the volume of your liquid. We'll now start making measurements similar to those which you're going to do in this experiment. First of all, we'll measure the density of a regular cylindrical object. And to get the density, then we will have to measure its mass and also its dimensions, namely its diameter and its height, so that we can use the geometry here of volume equals pi radius squared times the height or the length of the cylindrical object. The object which we'll be using here is a paperclip, which we've just straightened out so it looks more like a cylinder than a trombone. To measure its mass, we will use this electronic analytical balance. Now remember, it must be level and read 0, and so then we can open the door, put the paperclip on the pan, close the door, and read the mass of our paperclip. The length of this stretched out paperclip is 10.68 centimeters. You must read between the lines when you are reading graduations. Because of the thinness of this wire, measuring its diameter is a little bit more difficult, but I would read this to be about 0.8 millimeters. But remember, an error probably up to 10% is possible. Crunching the numbers gives a density of about 8 grams per cc for our paperclip. But of course, the crude measurement of the diameter could lead to a significant error. In our next density measurement, we will measure the volume of a solid by its displacement of water. An object which sinks in any liquid displaces its volume of that liquid. And here we'll be using water, and as you can see, we filled a graduated cylinder to the 6.00 milliliter mark. Now when we put the solid in, if it sinks and does not dissolve, it will displace water equal to its volume. We'll again be measuring the density of paper clips, and here we are weighing out 14 paper clips, and they weigh 6.1559 grams. Here's a close-up of our graduated cylinder with the water in it, and as you can see, the bottom of the meniscus is exactly on 6.00 milliliters. We've now put the 14 paper clips into the graduated cylinder. We're very careful to make sure that there were no bubbles. We made sure that all of those bubbles got out, and now you can see the level of the liquid is no longer at 6.00 but 6.80. So the volume of these paper clips is 0.80 cc's. The density of these paper clips then is given simply by their mass divided by the volume of the water that they displace, which is about 7.7 grams per cc. Our final experiment then will determine the density of paper clips using a pycnometer. The pycnometer is a container. It contains a stopper as well. Well, the stopper has a hole on it. This container contains an exact and reproducible volume of a liquid. Now the stopper has a hole in it so that when you put the stopper on, excess liquid will squirt out and you will have the exact volume that you are supposed to have in the pycnometer. Well, to start out with, we're going to weigh the pycnometer while it's still empty. Yeah, it looks pretty good. The balance is zeroed. It's level. We'll put the pycnometer on, and here's the weight of the empty pycnometer. We put the paper clips into the pycnometer and the weight is now 56.3626 grams, and we now know the weight of the unknown which we are measuring. We will now put water in this flask with the paper clips here. This water that we're putting in is going to tell us the volume that we have here. And we'll fill it all the way to the top, put the stopper on, and then shake very vigorously so that all the air bubbles or anything else which is not water gets knocked out. We're pretty good here. Let's just try one more time. We will take this off and we'll fill it up again all the way to the top. Put the stopper on the pycnometer, give it another shake, and I think that looks pretty good. We'll dry it off and weigh it. And now we have the weight of the pycnometer with all the water it can contain while the paper clips are still in it. Finally, we have the pycnometer completely filled with water. This weighing and the weighing of the empty pycnometer will give us, after using the density of water, the volume that this pycnometer contains. The last measurement we need is the temperature of the water we are using. For this, we'll use our thermometer. And the temperature of this water is 26.8 degrees centigrade. We'll need this temperature to convert the weights of water we have measured to volumes in order to determine the volume of the paper clips. Now let's recap what you did in this pycnometer experiment. We show here 4 pycnometers, but actually they represent the 4 weighings of your pycnometer. This is the empty pycnometer. This is the pycnometer with the unknown paper clips in it. This is the unknown paper clips plus the water, and this is the pycnometer filled with water. Note we put red dye in the ones with water so they could be more easily seen. To get the mass of the unknown solid, we subtract these 2 weighings. To get the mass of water filling the pycnometer, we subtract these 2 weighings. Now note, the mass of water filling the pycnometer can be converted into the volume filling the pycnometer by dividing by the density of water. Subtracting these 2 values gives the mass of water when the paper clips are in the pycnometer. If you use the density of water, again you will get a volume of water. Subtracting the volumes of water in these 2 flasks gives you the volume of the paper clips. Pouring the liquids from each of the weighings into a graduated cylinder shows that the difference in volumes you have here is actually the volume of the paper clips that you had in the pycnometer. Another way of putting this is that had you taken the pycnometer completely filled with water and put in the paper clips, then the volume of water which would have spilled out is a difference in volume between these 2 columns of water. Now remember, when you take a solid and it sinks in a solution, the volume of water or solution displaced is equal to the volume of the solid. Here are the calculations. I hope you understand them. Recall that you made 4 weighing measurements with the pycnometer. From these you can determine the mass of the solid in the pycnometer. And also you determine the masses of 2 different volumes of water. The masses were then converted to the volumes of water by using the density of water, and the difference between these 2 volumes gave you the volumes of the solid in the pycnometer, namely the paper clips. The bottom line then is that the results here support the conclusion that paper clips are made of galvanized steel. In this experiment, you will also measure the density of a liquid unknown. Well, I'm just thinking, you ought to have a little bit of excitement in your life. And so